Welcome to another video on Markov processes. Last time we learned about the Markov property, which is the future is independent of the past given the present. And this present was a fixed time which was called t. And today we're going to learn about the strong Markov property. And there it's basically the same thing. The only difference is that this present is a random time, it's a stopping time. So is it still true that for a Markov process, the future of a stopping time is independent of the past of the stopping time given the present state at the stopping time? That's not always the case, but, well, very often, as we will learn. So, the strong Markov property. Remember that we had the optional stopping and sampling theorem where we asked ourselves if something is true for martingales at fixed times, is it also true at random times, stopping times? And the same applies here, but with the Markov property and the strong Markov property. So if in this equation here, the S here is a fixed time, then we would simply have the Markov property. Because the right-hand side only depends on xs, but nothing else. But the question is, if the same equation here also holds at stopping times. And if that's true, we call the Markov process a strong Markov process. Well, equivalently here, so what's the probability to be in some a at some time t after a stopping time? Given all the paths of the stopping time, that's the same as starting at xs and waiting for some time t. Equivalently, we can again, rather than saying x is in some set a, evaluate f of x for all possible f's here. Okay, first of all, everything is rather simple if I is discrete, because then every Markov process is a strong Markov process. And the reason is as follows. The calculation is actually not that hard. Let's use the second property, xs plus t, where s is now a stopping time, over some set A, which is in Fs, like this here. We can distinguish all cases expectation of f of xs plus t over the set A if capital S equals small s. Yes, so that's the same sum expectation now on the conditional expectation. So this here is in Fs. So I can condition the same thing here, f of x s plus t on Fs, but actually that's the same as on xs because I have the Markov property, like this thing here. This here is Ts s plus t f of xs. And actually, since I'm here on the set capital S equals small s, that I can also write a small s here. And then that's the same thing, or a small s or capital S does not matter. So I want to write a big S, I want to write a capital S here. Because then if I'm summing over all small s's, all what happens is that the the sum goes away and have the expectation of t capital S plus t, exchanging all small s's to capital S's, f of x capital S over the set A. And that means I am done, because then well, the left-hand side by definition is the same as the expectation of the conditional expectation of this thing here, and the right-hand side is again an x as measurable random variable, an x as measurable random variable, like so. And we are done with this proof here. Another case, which is simple, is if time is continuous. Now time is here continuous, but we need something. We need that, this here is a continuous function. So that's a function on the state space. That's continuous, and the map which maps S to this thing here is also continuous. Then X is also strong Markov. And the proof is the following. We had once that we can approximate S, the stopping time, by stopping times Sn, where Sn, they only take, where all Sn take only discrete values. Because then we can use the other result that we just had. And XSN converges to XS because X has right continuous paths. So this is true. And we can write the expectation of f of x s plus t conditional on fs. We have to show that we can exchange the fs here by an xs. Well, there's a limit, lim n to infinity. Expectation of, well, we are approximating from the right. We can use here f of x sn plus t conditional on fsn conditioning on fs. So this is true here because conditioning on fs, that's a small sigma algebra. That's exactly this what we have here. But I'm writing it like this here because here Sn only takes discrete values, so we can work with the result we just had on the last slide. We can exchange the f by the x here. So that's the same as exchanging the f here by xSn. And then we know the continuity things, which means, well, this thing here is continuous in the first coordinate, so it converges to the same with the s. And that function here as a function of this variable is also continuous, so we also need the continuity of the first thing here. And then we can write, no, we can ignore the limit. We can write that's the same as t. Right, so this here is t sn plus t f of x sn. We need all the continuity things. And that then converges to t s plus t f of x s. And that's also f as measurable, so we can forget about the outer condition expectation. And we are done because we have shown the property, what we need for the strong Markov property process, for the strong Markov property. Well, two things. Poisson point process and Brownian motion are strong Markov. And all we need to change, because paths are right continuous in these two cases, if the continuity things here apply. So if this here is a continuous function, and if S maps to this is continuous. But this thing here, we computed it. That's this expectation. So this is certainly continuous in S because it's a constant in S. And if f is continuous, the right-hand side is also a continuous function. Yeah, because f is bounded, we can use a sequence here and use some convergence result in order to see that this here is a continuous function in x. And the same applies to Brownian motion, only the formula is a bit different, like this here, but again, okay, it's not a, is it a constant function in S? Well, maybe not. Well, okay, that was wrong. P depends on S, so that's not a constant function, but it's a continuous function in S. And the same applies here, so this is a continuous function in S. If f is also continuous, and if f is continuous and bounded, then this is also a continuous function in x. So in both cases, we have that these two properties hold, and then we have shown x is strong Markov, and therefore Poisson point process and Brownian motion are strong Markov. And actually, it's not really easy to construct a Markov process which is not strong Markov, but here's one example. I'm drawing a picture. I have a random time t here. Up to this random time, it's 0, and afterwards it increases with slope 1. So this is this process here. This thing here has an exponential 1 distribution, for example. And by this reason, we have a Markov process. So that's the first thing. So it's a Markov process. I can write down its transition property like this here. So between S and S plus t, what happens? When it starts in x equals 0, well, you have to wait. You have time increment t, so you you have to wait, and t is an exponential time, which means it's memoryless. So you have the same waiting time t when you start in time s, if x equals 0. But if x is bigger than 0, well, you know that t already happened, so it just increases linearly. So that's the transition operator. We also assume that ft here is complete. We have to assume this, which is this one of this usual conditions that we had in the martingale part of our course. Because we're doing this because then, this set here, t equals t, is a null set, and therefore in ft. Now, I'm using the stopping time s equals t, so I'm using t basically. Certainly, a time small t after the time it increases here, well, I just have f of t, there's no question, because s is exactly the stopping time. On the other hand, when you simply use this formula here and you're using the capital S here, that's something different then. Because at xs is 0, because at time s, xs is still 0, it just goes out of 0 very slowly. So this here is, well, the first part, that's this. So this expectation. And that's not f of t. So that's not equal f of t, which would be the case if it's strong Markov, because that we've just shown that this here is unequal to this. Therefore, this process is not a strong Markov. Okay, that's it for today. And next time we'll continue with the so-called Chapman-Kolmogorov equations for Markov processes. See you then.